Yes, good morning, students. In this session, I am going to complete nuclei. I'm going to complete nuclei in this session. Whenever we take any element is represented with the X. Z is called as the atomic number, means number of protons. A is called as the mass number, means number of protons plus neutrons. So if you want number of neutrons, we have to take N is equal to A minus Z. Number of neutrons is equal to mass number minus atomic number. For example, oxygen 816 if you take, in this number of protons are 8. If you want number of neutrons, 16 minus 8. So number of protons are 8, number of neutrons also 8. Like this we may take for any element. Right? So then whenever we take these elements can be classified as isotopes. Atoms of the nuclei having the same atomic number with a different mass number. What is that? Z is called atomic number, A is called as mass number. Atoms of the nuclei having the same atomic number with different mass number are called as the isotopes. Atoms of the nuclei having the same atomic number with a different mass number are called isotopes. H11, 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 H12, H13. These are the isotopes of the hydrogen. Next, oxygen 816, oxygen 817, oxygen 818. These are the isotopes of oxygen. Like atoms of the nuclei having the same atomic number with a different mass number are called isotopes. Next, isobars. Isobars. Atoms of the nuclei having same mass, same atomic number. Atoms of the nuclei having the same mass number with a different atomic number. Same mass number, X, Z, A. Z is the atomic number, A is mass number. Same mass number should be there. So atoms of the nuclei having the same mass number with different atomic number are called isobars. Carbon 614, nitrogen 714. These are the isobars. Next, isotopes. Atoms of the nuclei having the same number of the neutrons are called isotopes. Equal number of neutrons will be there. So nitrogen 717, oxygen 818, fluorine 919. See, 17 minus 7 will be 10. 18 minus 8, 10. 19 minus 9, 10. Like atoms of the nuclei having the equal number of neutrons are called as isotopes. Next, isomers. Atoms of the nuclei having the same number, same mass number, same atomic number with a different radioactive properties. With the different radioactive properties are called isomers. So bromine 3580, either in a ground state or in excited state, we'll take bromine 3580 only. 3580 we will take it. These are called isomers. This is related to the concept. Next, mass of the nucleus. Every nucleus consists of the same mass. That will take mass of the every nucleus, that will be same. So mass of the nucleus is independent on Mass of the nucleus is independent of this mass number. For it will be density of the nucleus will be same for all elements. Density of all the elements will be same. So whenever we take that, one unit is there to measure the mass, AMU, atomic mass unit. One atomic mass unit is equal to 1.67 into 10 power minus 27 kg, 1 unit. Or one atomic mass unit is equal to 931.5 million electron volts, MeV, 935 billion electron volts. Like this, we may take. So atoms, to measure that subatomic particles mass, we use another unit called as the atomic mass unit. It is the 1/12 of carbon 612 atom. 1/12 of the carbon 612 atom it is. Okay. So we can express the mass of the electron in terms of the atomic mass unit. We may express that mass of the electron in terms of atomic mass unit. So 5.4 into 10 power minus 4 AMU, atomic mass unit. 5.4 into 10 power minus 4 AMU, atomic mass unit, we'll say that. This is the mass of the electron. Then mass of the proton, if you want, that will be 1.007276 AMU. If you want mass of the neutron, it will be 1.0000866 AMU. This is the mass of the neutron. Mass of the neutron it is. Okay, this is related to this. Next. Volume of the nucleus is directly proportional to mass number. Volume of the nucleus is directly proportional to mass number. That we will take. Volume is proportional to A. From this we'll write volume of that nucleus is taken as 4/3 pi R cube is proportional to A. From this we will write R cube is proportional to A. Then R is proportional to A power 1/3. R is proportional to A power 1/3. To replace this proportionality, we will take a constant. R is equal to R0 into A power 1/3. R is equal to R0 into A power 1/3. This we will take. R is equal to R0 into A power 1/3. So where R0 is that, one constant 1.2 into 10 power minus 15 meters. R0 is the constant. It is 1.2 into 10 power minus 15. So when we take the density of the nucleus, rho is equal to 3m divided by 4 pi R0 cube. R0 cube is this 1.2 into 10 power minus 15. And then density will be equal to 2.38 into 10 power 17 kg. In the previous CET, they have asked what is the order of the nuclear density. Order of the nuclear density is in the order of 10 power 17 we have to write. The nuclear density is in the order of 10 power 17 kg. The order of 10 power 17 kg per meter cube. 10 power 17 kg per meter cube. This is the order of the nuclear density. This is the order of nuclear density we'll take. Again, this radius R is proportional to A power 3 is there, A power 1/3 is there, that we will write. Radius of the nucleus is directly proportional to A power 1/3. What is A? A is called as the mass number. Then we may write surface area. Surface area is directly proportional to r square, because surface area S is equal to 4 pi r square. Okay, surface area is directly proportional to r square. Therefore, S1 by S2 is equal to, otherwise R1 by R2 if I write, R1 divided by R2 if I write, it will be equal to S1 divided by S2 whole power on right. Or if you want, write that in the order of R by R1 by R2 is equal. In the place of S1 by S2, we may write A1 divided by A2. A1 divided by A2. This is proportional.
One by 3 ಆಗ್ಬೇಕಲ್ಲ sir ಇಲ್ಲಿ.
This also there. Then we may write this. S is proportional to R. Then S1 divided by S2 is equal to, R1 is there. So R1 by R2 whole square is there. Therefore, S1 by S2 is equal to, and the R is proportional to A. R is proportional to A power 1 by 3. Then we'll write R1 by R2 is equal to, R1 by R2 is equal to A1 divided by A2 whole power 1 by 3. That we'll write. Instead of R1 by R2, we may write A1 divided by A2 whole power. This is square is there. So 2 divided by 3 we will write. Because R1 by, in the place of R1 by R2, we'll write A1 by A2 whole power 1 by 3. So this square is there. So S1 by S2 is equal to A1 by A2 whole power 2 by 3 we will write. This is one. Again, in the previous years, latest the previous means about 2016 or 17 they have asked it. So the volume of the nucleus is directly proportional to, volume of the nucleus is directly proportional to mass number. So V1 divided by V2 is equal to A1 divided by A2. Or mass of that nucleus M is proportional to cube of the radius. Then this they have asked, M1 by M2 is equal to R1 divided by R2 whole cube. This is, and whenever we take that velocity is that, let us suppose a body is moving, then a body is at rest. It splits into two parts of masses M1 and M2. These parts, they are moving with velocity V1 and V2. Then according to law of conservation of linear momentum, total momentum before collision is equal to total momentum after collision. M1 V1 plus M2 V2 we will take. So therefore, M1 V1 is equal to, minus will be there, minus I am not taking. So M1 V1 is equal to M2 V2. Otherwise, we'll write that M is inversely proportional to V. Otherwise, V is inversely proportional to M. Anything we may write. So V is inversely proportional to M we will take. V1 by V2 is equal to M2 divided by M1. Based on this formula, problem is there. I will explain in this session. Right? Based on the first formula also, problems are there. This is regarding that isotopes, isobars, and the radius of the nucleus, all this. Then whenever we go for that Einstein's mass energy relation, Einstein's mass energy relation. Mass energy relation. E is equal to mc square. E is equal to mc square. E is equal to mc square. Then we may write that energy E is equal to mc square. This energy, if you want to convert mass into square of the speed of the light, what is C here? C is 3 into 10 power 8 meters per second. So then we will take that. One atomic mass unit, if you take that, one atomic mass unit, if you take that, E is equal to 1.66 into 10 power minus 27, 10 power minus 27 into speed of the light. That will be equal to 3 into 10 power 8 whole square. There we will write energy E is equal to 1.66 into 10 power minus 27 into 9 into 10 power 16. That on simplifying we will get 14.94 into 10 power minus 11 joules. This is the energy. So this energy of these taken, energy of this is taken. Then if you want energy of the energy in the 14.94 10 power minus 11 joules. If you want this energy in electron volts, if you want this energy in electron volts, we have to divide with energy E is equal to 14.94 into 10 power minus 11 divided by 1.6 into 10 power minus 19. It is in electron volts. It is taken as electron volts. If you want that million electron volts, we have to multiply with 10 power 6. If you want that in million electron volts, we have to multiply with 10 power 6. So then energy is taken as 931.5 million electron volts. Okay, so this I want only this one. Energy is equal to what? 931.5 million electron volts. This is only I required. This part is not required for me. So this conversion I have explained. That's all. Next. Then mass of the electron, we know it. So energy of the electron, whenever you want to take that. So energy of the electron E is equal to mass of the electron I have explained in terms of the atomic mass units. 5.4 into 10 power minus 4 AMU, atomic mass unit. Then mass of the then E energy of the electron, if you want, so 5.4 into 10 power minus 4 into 931.5. 931.5 it is. So 5.4 into 10 power minus 4 into 931.5. So energy of the electron will be 0.512 MeV. 0.512 MeV. Like energy of the proton, energy of the neutron, we may take that. Energy of the proton is equal to 938.27 MeV. Energy of the proton is 938.27 MeV. This they have asked, that's why I am explaining. So energy of the neutron is 931.56 million electron volts MeV. These are the energies of the electrons, proton, neutron. Like, okay, binding energy. First we'll take that mass defect. It is the ratio of the, it is the difference between the mass of the nucleus and mass of the nucleus. Let us suppose this is the nucleus. It's called as the nucleus. When we measure that whole mass of the nucleus is capital F, on splitting it into lighter nuclei, splitting it into protons and neutrons. Individual nucleons will say that. These are taken as protons and these are taken as neutrons. So a nucleus that is split into constituent nucleons called as protons or neutrons. Individually, if we measure mass of the protons plus mass of the neutrons, is not coinciding with the mass of the total nucleus. The difference between the mass of these protons and the neutrons individually is more than that of the mass of the nucleus. Mass of the nucleus is showing that mass of the individual nucleons. The difference in that mass is called as the mass defect. So the difference between the mass of the nucleons and the mass of the nucleus is called as the mass defect. So mass defect, it is represented with the delta M. Delta M that we may express in terms of kgs, or in terms of the atomic mass units. I have explained up to now atomic mass units of these electrons, protons, neutrons. Okay, mass defect is that mass of the nucleus and the mass of the nucleus difference. So ZMP, mass of the all protons. Next, A minus Z into Mn, mass of all the neutrons. So this will give mass of the protons, total mass of the protons and the neutrons. This is the mass of the nucleus. The difference between mass of the protons plus mass of the neutrons with mass of the whole nucleus is called as the mass defect. Mass defect is taken as delta M. This mass defect we may express in terms of atomic mass unit, AMU, or we can express in terms of the kgs. This mass defect we may say in terms of atomic mass unit. How we'll get atomic mass unit? In terms of this mass of the proton. Mass of the proton, we will take that 1.67 into 10 power minus 27 kg we will take. Okay. Instead of this, we may take mass of the proton. We may take 1.007276 AMU. So we may take like this. We may take like this, or we may take like this. If you take in terms of kgs, the mass defect will be in kgs. If you write this mass of the protons and mass of the neutrons in the atomic mass units, we will get mass defect in atomic mass units, right? It is required. Why? In binding energy, we write the mass defect. What is binding energy? Binding energy. This is the energy required to combine all the nucleons. Individually, protons and the neutrons are there. We have to combine that into a single nucleus. The amount of the energy required to combine all the nucleons into a single nucleus is called as the binding energy. So the energy required to combine all the nucleons to form a single nucleus, or the energy required to split that. It is a nucleus. Let us suppose it is the nucleus. This nucleus, if you want to split into constituent nucleons, when we want to split this nucleus into constituent nucleons, the amount of the energy needed is called as the binding energy. The amount of energy is called as the binding energy. So the binding energy BE is equal to, binding energy BE is equal to delta M into C square. This we will write. If mass defect is delta M is in kgs, we will write this. If that binding energy per nucleon, if mass defect is in kgs, this is the unit. So binding energy BE is equal to delta M into 931.5 million electron volts. That we will take. If delta M is atomic mass units, if the delta M is atomic mass units, this we have to use. If mass defect is in atomic mass units, this is the formula to calculate binding energy. If the atomic mass unit is in kgs, this is the formula to calculate binding energy. So this specific binding energy will be there. Binding energy per nucleon is called as the specific binding energy. So based on the specific binding energy, stability of the atoms, stability of the elements will be there. Whenever we plot the graph between the mass number and binding energy per nuclear, binding energy per nucleon is taken like this. Binding energy per nucleon is taken like this. And mass number is taken like this. Okay. So binding energy per nucleon is like this and mass number is like this. So then binding energy per nucleon will be like this. So if the peaks will what's called the peaks or like that, it will be there. This is helium, lithium, like helium, lithium, beryllium, boron, like that. Beryllium, boron, carbon, nitrogen, like that it will be there. So these elements whose binding energy per nucleon, if it is less, they are less stable. As the binding energy per nucleon is less for these elements, they are less stable. For their stability, they combine and forms two or more lighter nuclei, they combine and forms a heavy nucleus. That process is called as the nuclear fusion. The process of combining two or more lighter nuclei to form a heavy nucleus is called as the nuclear fission. So the binding energy per nucleon is more, especially for the iron. Binding energy per nucleon is binding energy per nucleon is 8.75 million electron volts. 8.75 million electron volts will be there. They are more stable. So with binding energy per nucleon, that is more for the elements which are about 28 mass number, about 28 to 170, like that. So if the mass number is more for the elements, if the mass number is more for the elements, they are less stable. If the mass number is more or mass number is less, they are less stable. The elements whose mass number is about greater than 170, they are unstable. Means what? They are not stable. Then if they are not stable, for the stability, what they'll do? The elements whose mass number is greater than 170, they are unstable. So 1 to 30 elements, 1 to 20 elements, they, let us suppose these are 1 to 20 elements, they are less binding energy per nucleon will be there, less stable. So the elements whose mass number is greater than 170, they are less stable. They are unstable. For their stability, they will split. A heavy nucleus that splits into two or more lighter nuclei. That process we call it as the nuclear fission. The process we call as the nuclear fission. The process of splitting of heavy nucleus into two or lighter nuclei is called as the nuclear fission. So whenever we take the nucleus, in the nucleus, nucleons called as nucleons are called as protons and neutrons will be there. So these in between the nucleons, whenever you take the force will be there between the means both that proton that will attract, proton and the neutron will attract, and neutron and neutron will attract. So force of attraction will be there, proton to proton, neutron to neutron, or proton to neutron. That means nuclear force is independent on the charge, because proton is possibly charged, neutron is chargeless. So nuclear force is independent on the charge. Then a proton permanently be a proton in the nucleus. A neutron in that nucleus is permanently, it will not be that nucleus. So proton and neutron, they will be convertible. Proton becomes a neutron, neutron becomes proton. By exchanging the mesons, they'll exchange the mesons. By exchanging of the mesons, the proton becomes a neutron and the neutron becomes a proton. This is called as, that is a, these are dependent on spin. These protons, these nuclear forces are independent on the charge and dependent on the spin. And nuclear forces are not centralized forces. They will be there. Let us suppose one proton here and one proton here. Attraction will be there. One proton, neutron is there. One proton is there. Attraction will be there. So nuclear forces are not the centralized forces. Next, nuclear forces are the saturated forces. Saturated forces means one proton, it will attract the surrounding protons only. It won't attract all the protons in the nucleus. That's called saturation force. So nuclear forces are the saturation forces. And the nuclear forces, they are what's called, they will exchange the mesons. They are exchange forces. So pi mesons they will exchange, and proton becomes neutron, neutron becomes proton, like this. Next, when we come to this radioactivity, it is that phenomenon of emitting alpha, beta, and gamma. Alpha, beta particles and gamma is radiation. The spontaneous phenomenon of emitting of alpha, beta particles and gamma radiation is called as the radioactivity. So when the radioactive substance that disintegrates by emitting alpha, beta particles and gamma radiation, that we call as the radioactivity. It is a spontaneous phenomenon. See here, whenever these emitting the decay based on that alpha it may release, or beta it may release, and gamma means radiation it may release. So alpha decay will say that most important, this is based on the alpha decay, protons are there. Alpha decay. In the case of the alpha decay, atomic number and mass number, they'll be changed. So what happens in that alpha decay, XZA, it is the element. Then that gives rise to Y, Z minus 2, A minus 4. Atomic number is reduced by 2 units and mass number is reduced by 4 units in the case of the alpha decay. Alpha particle is nothing but helium nuclei, helium-24 in this. Helium-24, in this energy Q is released. So XZA, that gives rise to Z minus Y into Z minus Y, Z minus 2, A minus 4. So a nucleus, whenever it splits, whenever it decays, then it releases the alpha particle. In the case of alpha particle, atomic number is reduced by 2 units and mass number is reduced by 4 units. Atomic number is reduced by 2 units and mass number is reduced by 4 units. This is alpha decay. So example, whenever we take that uranium 92 238, if you take uranium 92 238, if you take in that thorium, from that it will be released thorium. That gives rise to thorium, TH, thorium 90 234 plus heat energy, helium-24. Along with that heat, Q is released. Okay, this will happen in the case of the alpha decay. And when we go for the beta decay is of 2 types. Positive beta decay is there, negative beta decay is there. Okay, alpha decay is important. This, along with that example, you have to practice. Next, beta decay. So beta decay is of 2 types. This beta decay, we'll say that beta decay, this is a positive beta decay and a negative beta decay. In the negative beta decay, electron will be released. In the positive beta decay, positron will be released. This will happen. Then we'll see. Next, negative beta decay I am taking. Negative beta decay. Negative beta decay. So then in the negative beta decay, what happens? Electron will be released. XZA, that gives rise to Y, Z plus 1, Z plus 1A, plus E minus 1, 0, plus anti-neutrino, along with that energy, anti-neutrino it is. Anti-neutrino along with that energy will be released. So example, if you take that XZ, carbon 614, that gives rise to nitrogen 714, plus E minus 1, 0, plus neutrino, anti-neutrino plus energy. This will be negative beta decay. In the case of the positive beta decay, then atomic number. In the case of atomic number, that is reduced by 1 unit. Mass number that remains same. So let us suppose X, Z, A, that gives rise to Y, Z minus 1, A plus E plus 1, 0 plus neutrino plus charge Q. Then if you take this is nitrogen 713, that gives rise to carbon 613 plus electron positron E plus 1, 0 plus neutrino plus energy Q. This will be reduced. NZ30 that gives rise to carbon 613 plus E plus positron. This is called as the beta decay. So in the case of the gamma decay, atomic number and mass number, they won't be changed. In the case of the gamma decay, atomic number and mass number, they won't be changed. So what happens? Only radioactive property will be different. So nickel, before gamma decay, either positive beta decay or negative beta decay takes place. So nickel 2880, that will be same 2860, it is 80 not 2860, that will be same either excited state or in the ground state, but radioactive properties are different. It will release that energy while it is coming from the higher energy level to that ground state. So with the same atomic number and mass number, these will be there. These are the alpha, beta, gamma decays. Next, if we take that half-life period. The time taken to disintegrate half of the existing elements, half of the existing nucleus is called as the half-life period. So the time taken to disintegrate half of the existing, let us suppose it consists of 1 lakh nuclei are there. This 1 lakh to become 50,000, how much time it takes? That is called as half-life period. This 50,000 to become 25,000, how much time it takes? The time period is called as one more half period. This 25,000 should become half of that existing, 12,500. Then one more half period is taken as the half period, like that. So half-life period is the time taken to disintegrate half of the existing radioactive nuclei. We'll say that half-life period is equal to 0.693 divided by lambda. This is the half-life period. Then whenever we take that average lifetime is equal to 1 by lambda. The total time for disintegration of that all radioactive nuclei, total lifetime divided by total number of the nucleus is called as the average lifetime. This is called as the average life period. So if you want that time taken for n half-lives, if it is taken, t is equal to n into t half. So time taken for n half-lives, t is equal to n into t half. So number of half-lives, if you want, t divided by t half. This is also important. Number of half-lives, n is equal to t divided by t half. Otherwise, n is that number of nuclei at any instant of time by n naught. N by n naught is equal to mass. Initial mass is taken as m naught, and the mass at any instant is taken as m. That is equal to m by r. Activity a divided by a naught is equal to. For all of this, we will write 1 by 2 power n. 1 by 2 power n it is. So n by n naught is equal to 1 by 2 power n. We may write that what is n? N by n naught is equal to 1 by 2 into this n will be equal to t half. T is equal to n into t half. then T is equal to, sorry, N is equal to T divided by T half. Therefore, we will write N divided by N naught is equal to, this is T divided by T half, we will write T divided by T half. T divided by T half, like this. Like this we will take, right? So then we'll come to the radius of the nucleus is 10 power minus 15 meters. Size of the nucleus is 10 power minus 15 meters. So that is called as 1 Fermi. 1 Fermi is equal to 10 power minus 15 meters. Then we'll say activity means radioactivity. Activity is measured in Curie. Curie is the unit of activity. Becquerel, Rutherford, Curie, Rutherford. So Curie, Becquerel, and Rutherford. These are the units. These are the units of the radioactivity. Fine, we'll come to the problems part. Which one of the following particles are constituents of the nucleus? Which one of the particles are, which one of these are the constituents of the nucleus? So these are protons and neutrons are the constituents of the nucleus. Protons and neutrons are the constituents of the nucleus. Right. Next. The particles which can be added to the nucleus of an atom without changing its chemical properties. The particles which are the particles which can be added without changing the chemical properties are neutrons. On adding the neutrons, chemical properties, they won't be changed. So neutrons, that will say. Next. The neutron was discovered by James Chadwick. Proton was discovered by Rutherford, and electron was discovered by J.J. Thomson, and this neutron was discovered by James Chadwick. The mass number of the nucleus is so mass number that may be more than or that may be less than, it will be there. Mass number of the nucleus is sometimes more than that of and sometimes equal to its atomic number. So always need not be more. That may be equal also. Oxygen 816, if you take, what happens? Oxygen 816, that's a double is there. So sometimes mass number of the nucleus that may be more than. Or sometimes equal also, sometimes. So like that we will take. Next. The energy equivalent to 1 kilogram of matter is, so mass is taken as 1 kg. According to Einstein's mass energy relation, E is equal to mc square. Therefore, E is equal to, what is M? 1 kg into C is what? 3 into 10 power 8. S square is the whole square, we'll write. Therefore, energy E is equal to 3 3s are 9. 9 into 10 power 16 joules. 9 into 10 power 16 joules. 3 3s are 9. This is option is not there now, and that. But in such case, what we have to do? 10 power 16 is not there. So this is 9 is identically equal to 10. 9 is 10 identically equal to 10. Therefore, E is taken as identically equal to 17. 10 power 17. That's why this is the correct answer. So 9 is identically equal to 10. Nearly 10. That's why we'll write 10 power 17 joules. Nuclear binding energy equivalent to mass defect, nuclear binding energy will be equivalent to mass defect, we'll say. Mass defect of the nucleus. Nuclear binding energy is equivalent to mass defect of the nucleus. Next. The binding energy of the deuterium is 2.23 million electron volts, and the mass defect is given in atomic mass units. We have to calculate that mass defect in atomic mass units. Simple. It is given as a million electron volts. That's why that we have to take in atomic mass units. This is mass defect. Delta M is equal to. This is what binding energy. Binding energy B divided by 931.5. So 931.5. 931 is sufficient. 931. So delta M is equal to binding energy how much? 2.23 divided by 931. Right. So on simplifying this, we will get 0.0024. 0.0024, first option. This is decreases. This mass decreases. That's why negative sign it is represented. No. Decrease that we don't say. That will say difference only we are saying. That's why negative sign we should not use. Only we have to say that difference. Mass defect means what difference. Then we'll take positive sign out. 0.0024. Fourth option is correct. Negative sign we should not take. Next. Which of the following has the mass closest in the value of the positron? So positron is nothing but antiparticle of the electron. Positron is the antiparticle of the electron. That's why electron mass, positron mass almost the same. The size of the nucleus is in the order of. Size of the nucleus is in the order of 10 power minus 15 meters. 10 power minus 15 meters. Next, during a beta decay, a neutron in the nucleus decays, emitting an electron, a positron. Okay, during the beta decay, a neutron in the nucleus decays by emitting an electron. During the beta decay, an electron will be either electron or positron will be emitted. That I have explained just now. So a neutron in the nucleus decays by emitting and decays and emits an electron. In the beta decay, either electron or positron will be released. Electron or positron will be released. Next, 11th one. Next one is 2 protons are kept at a separation of 10 nanometers. Let F and F be the nuclear forces and the electron. Fe, that is actually printing mistake. It is Fn. Fn and Fe are be the nuclear forces and the electromagnetic forces. So whenever we take that, the gravitational forces are very weak. This nuclear force means electromagnetic forces. Electromagnetic forces are about 10 power 36 times greater than that of the gravitational forces. So these the nuclear forces are about 10 power 38 to 10 power 42 times greater than that of the 10 power 42 times greater than that of the gravitational forces. So much more gravitational electrostatic forces are electrostatic forces, gravitational forces whenever we take that. So gravitational force is less when compared with the electrostatic force. These are less when compared with that strong nuclear force. This is called as the strong nuclear force. Yes, and first more strong nuclear force. So what did they ask? This is Fn and Fe. Fn and Fe. So the electromagnetic forces. So this nuclear force is much greater than that of the nuclear force is greater than that of the much greater than that of the Two protons kept at separation 10 nanometers. Let Fn and F be the nuclear forces and the electromagnetic forces. Then two protons are kept at separation 10 nanometers. Okay, fine. The two protons are kept at separation 10 nanometers. If Fn be the nuclear force and the electromagnetic forces between them. Nuclear forces are greater than that. Nuclear forces are greater than that of the electromagnetic forces. Next. A radioactive element has a half-life period of 15 years. What is, you have to follow this. All these are previous years CET problems, 2021, 2020, 2018, like that I have taken back. So this a radioactive element has a half-life period of 15 years. What is the fraction that will decay in the 30 years? What is the fraction that decays in the 30 years? So a radioactive element has a half-life period. Half-life period is taken as T half is equal to 15 years. 15 years. Okay. What is the fraction that will decay in 30 years? So time period is given as 30 years. Then what is that half-life period? This is n half. The number of half-lives is equal to T divided by T half. T divided by T half. That is equal to T is given as 30 divided by 15. This will get cancelled 2 times. Number of half-life periods are 2. Number of half-life periods are 2. Therefore, fraction that remains n by n naught is equal to 1 by 2 whole power n. Whole power n. 1 by 1 by 2 whole power n. So then n by n naught is equal to 1 by 2 whole power. What is that? 2 is there. That means n by n naught is equal to 1 by 4. 1 by 2 whole square means what? 1 by 4. This fraction that remains n by n naught is equal to 1 by 4 or 0.25. 0.25. Fraction that remains is equal to 0.25. N by n naught is equal to, this is n naught. N by n naught is equal to 0.25. Like this we may take. Next one. Half-life period of the tritium is 12.5 years. Half-life period of the tritium is 12.5 years. Means what? T half is given. T half is equal to 12.5 years. What is the mass of the tritium of initial mass is 64 mg. Initial mass is given as a 64 mg. Then what is the mass that remains? M naught is given as 64 milligrams mg. It remains after 50 years. Time period is given as T is equal to 50 years. Then we have to take for half-life period. N is equal to T by T half. T by T half. N is equal to T is how much? 50 years. 50 divided by T half means what? 12.5. 12.5. That will, it will get cancelled 4 times. Therefore, n is equal to 4. Number of half periods are up. Number of half lives are 4. Then how much mass that remains after? How much mass that remains after these 50 years they have asked. So then we take this m by m naught. M divided by m naught is equal to 1 by 2 power n. 2 power 2 1 by 2 whole power n. Like this we write 1 by whole power n. There m by m naught. M is taken as what? 64. M is taken as a 64 mg. 64 mg. So then m divided by m naught is equal to 1 by 2 whole power. N will be equal to what? 4. That will be m divided by m naught is equal to 1 divided by 16. This is 1 by 16. Therefore, we will take m naught is equal to 16 into m. M is how much it is given? 16. I want m. M is equal to m naught divided by 16. Therefore, m is equal to m naught is how much? 64. 64 by 16. And 64, 16 will get cancelled 4 times. 4 times. So 4 mg. Answer is 4 mg. Right? I'm going to stop the class here. We will see that the rest of the concept in the next class. Thank you. I'm going to stop the class here.
Thank you, sir.
Thank you. Thank you. I will share the notes later. Please wait.